the first derivative test for monotonicity. Hello everyone. To begin, let's reflect on what we have already covered. In the previous subsections, we explored the graphical intuition, essentially how a graph looks when it rises or falls, as well as the formal analytical definitions of increasing and decreasing functions. Now, while those formal definitions are mathematically sound and precise, they are often impractical to use when we are dealing with complex functions. This is because the formal approach requires us to compare pairs of points across an entire interval, which can be incredibly tedious and time-consuming. To simplify this process and make our analysis more efficient, we can leverage the power of calculus. This leads us to the core of today's lesson, the first derivative test. This powerful tool allows us to determine whether a function is increasing or decreasing by simply analyzing the sign of its derivative. In the following slides, we will explore the logic behind this test and see exactly how to apply it to solve problems. Understanding the core concept. Now that we have established why the formal definitions of increasing and decreasing functions can be impractical, let's dive into the core concept that allows calculus to simplify this process. First, it is essential to remember that the derivative of a function, which we denote as f prime of x, represents the slope of the tangent line to the curve at any given point. To understand how this relates to monotonicity, consider the direction of that slope. If the slope is positive, it means the graph is climbing upwards as we move from left to right. On the other hand, if the slope is negative, the graph is sliding downwards, indicating a decrease in the function's value. And finally, if the slope is exactly 0, the graph is momentarily flat, meaning it is neither increasing nor decreasing at that specific point. Understanding this intuitive relationship between the sign of the derivative and the behavior of the graph is crucial, as it provides the foundation for the formal theorem we will examine in the next slide. Theorem 1, the first derivative test. Now that we have established the intuition that the slope of a tangent tells us whether a graph is climbing or sliding, let us look at the formal mathematical theorem that governs this behavior. First, we must define the necessary conditions for this test to be valid. We assume that we have a function, f, which is continuous on the closed interval from a to b, and is differentiable on the open interval from a to b. This ensures there are no breaks or sharp corners in the section of the graph we are analyzing. Given these conditions, the theorem provides us with 3 clear rules. First, the function f is considered an increasing function on the closed interval from a to b if its first derivative, f prime of x, is greater than 0 for every x in the open interval from a to b. In simpler terms, if the slope is always positive, the function is always rising. Second, the function f is a decreasing function on the closed interval from a to b if the first derivative, f prime of x, is less than 0 for every x in the open interval from a to b. This means a consistently negative slope indicates the function is always falling. Finally, the function f is a constant function on the closed interval from a to b if the first derivative, f prime of x, is equal to 0 for every x in the open interval from a to b. This describes a scenario where the graph is a perfectly horizontal line. While these formal definitions are essential for your exams, they can feel a bit abstract. To help you visualize this, I will use a real-world analogy involving a mountain hiker in the next slide. Real-world analogy, the mountain hiker. Now that we have established the formal theorem, let us use a real-world analogy to make these concepts more intuitive. Imagine a hiker walking along a mountain path from left to right. In this scenario, the hiker's altitude at any given point is represented by the function f of x. First, let us consider what it means for a function to be increasing. If the hiker's rate of change in altitude, which is essentially the slope of the path, is always positive, the hiker is constantly ascending. Conversely, if the rate of change in altitude is always negative, the hiker is constantly descending, moving downwards. Finally, if the rate of change is 0, the hiker is walking on a perfectly flat plateau, where the altitude remains unchanged. The crucial point to remember here is that in this scenario, this rate of change is exactly what the first derivative, f prime of x, calculates. By visualizing the derivative as the slope of a path, we can more easily apply the mathematical steps we will see in the upcoming example. Step-by-step application example. Now that we have established the theoretical foundation and the hiker analogy, let us apply these concepts to a practical example. We want to determine the monotonicity of the function f of x equals x squared minus 4x plus 6, specifically over the closed interval from 0 to 5. To begin, we move to step 1, finding the first derivative. As we discussed in the previous slides, the derivative gives us the slope of the tangent, which tells us the direction of the function. By applying the power rule of differentiation to x squared minus 4x plus 6, we find that the derivative, f prime of x, equals 2x minus 4. Next, in step 2, we need to analyze the sign of this derivative within our given interval of 0 to 5. To identify where the function changes direction, we first find the critical point where the slope is exactly 0. We set the derivative, 2x minus 4, equal to 0. Solving this, we see that 2x equals 4, which means x equals 2. Finally, in step 3, we use this critical point, x equals 2, to split our interval into two separate sections for testing. First, let us examine the interval from 0 to 2. We can pick any test point within this range, such as x equals 1. When we substitute 1 into our derivative, we get 2 times 1 minus 4, which results in negative 2. Since the derivative is less than 0, the slope is negative, meaning the function f of x is decreasing on the interval from 0 to 2. Now, let us look at the second interval, from 2 to 5. This time, let us pick x equals 3 as our test point. Substituting 3 into the derivative gives us 2 times 3 minus 4, which equals 2. Because the derivative is greater than 0, the slope is positive, and therefore the function f of x is increasing on the interval from 2 to 5. By following these steps, we have successfully mapped out the behavior of the function. In the next slide, we will discuss some common mistakes to avoid, particularly the tendency to confuse the value of the function with the sign of its derivative. Common mistakes to avoid. Now that we have walked through a practical example, it is crucial to discuss some common pitfalls. Let's look at the most frequent mistakes students make when applying the first derivative test. First, avoid confusing f of x with f prime of x. A common error is checking the sign of the original function, f of x, to determine if the graph is increasing. You must remember that the value of the function only tells you the position or the height of the point on the y-axis. To determine the direction of growth, whether the function is climbing or falling, you must look specifically at the sign of the derivative, f prime of x. Secondly, be careful not to ignore the interval. As we observed in our previous example, a function is rarely increasing or decreasing over its entire domain. It often changes behavior at certain critical points. Therefore, you should always clearly identify the specific closed interval from a to-be that you are analyzing before drawing your conclusions. Finally, do not neglect the requirement of continuity. If you recall the theorem we discussed earlier, the test requires the function to be continuous on the closed interval from a to-be if the graph contains a break or a hole, which we call a discontinuity. The first derivative test cannot be applied blindly across that gap, as the connection between the points is broken. Keeping these 3 points in mind will ensure your analysis is mathematically rigorous and accurate. Key takeaways. To conclude our lesson, let's summarize the key takeaways to ensure you have a solid grasp of this concept. First, remember that if the first derivative of f of x is greater than 0, it implies that the function is increasing. In practical terms, this means that as you move along the x-axis, the function's values are rising. Conversely, if the first derivative of f of x is less than 0, the function is decreasing. This indicates that the function's values are falling, much like the descent our hiker experienced in the analogy we discussed earlier. Ultimately, the most important thing to remember is that the derivative acts as a direction indicator for the function's behavior. While the original function tells you the position or height of a point, the derivative tells you exactly which direction the graph is moving.